Welcome back to the workshop. This lecture is going to be a bonus discussion simply because most of you won't have this lab project in your manual. However, it was in past manuals, and since 80%, 90% of all the videos that I'm going to throw in to this process are in one manual or the other, it's worth putting these in there just in case you have those older manuals that have the sequencer instructions. Now this was what one of the original manuals looked like. If you have one of these sets, it'll have the sequencer instructions in there. If you have this set, it'll have the sequencer instructions in there. If you have this big fat collegiate version, it will not have the sequencer instructions. It will not have the sequencer instructions in there. If you have the current set of RSLogix Studio5000 manuals, these do not have the sequencer instructions. And the reason that they don't is because most instructors and professors don't want to teach the sequencer instructions because no one really uses them anymore in new programs. However, if you're going to work in the arena, you're going to be working in plants that have older equipment in the installed base. Some of them use the sequencer instructions. These are not instructions that you want to meet for the first time at 2:30 in the morning out on the shop floor when the production manager is mad. He's not mad at you, he's just mad because no production is going out the door. And of course, you're the one that he thinks is holding up because you haven't fixed it fast enough. So if you don't have these lab projects, you can go ahead and watch the videos. You'll still get something out of them. So let's go ahead and look at the first of these. Bit shift left instruction, the BSL instruction. We began the first section in this manual talking about arrays. We had you create a 10-element array named any array, and those 10 elements are any array 0 through any array 9. When you look at the memory array, wherever these 10 double integers are at in the actual memory array, when you look at it as a physical space, when you look at it physically, it would be an array as you see in front of you, would be a stack of 10 double integers. Whether 0 is on the bottom or the top, it doesn't matter. The physical shape of the array would be 10 contiguous 32-bit double integers. The boundaries of this array would be from any array element 0, bit 0, in red square, to any array element 9, bit 31. That would be the boundary of this array. Although it is an array of 10 double integers, it is not an array of 320 bits. However, when you look at the 10 double integers as a contiguous chunk of memory, it is a field of bits. It is an array of 320 bits. And with the instructions that we're going to cover first in this manual, Beginner Plus, we are going to treat the bits in this array, when you look at these 10 double integers as 10 contiguous 32-bit elements in memory, we are going to treat them as a field of bits. We had you decrease the size of your array to 3 elements, 3 double integers. Any array 0, any array 1, and any array 2, elements 0, 1, and 2. So now you have a field of 96 bits. We are working with the bit shift instructions. A bit shift instruction is going to shift the value from one bit to the next bit, whether it's to the left or to the right. As you can see here in the top illustration, and remember what I told you in the manual, that when it comes to the bit shift left and bit shift right, left and right has nothing to do with your left and right. Now, on the screen here, it just so works out that it is your left and your right. Don't depend on that, especially in your logic. Don't be thinking your left and right, or left and right on the screen. Be thinking from least significant bit to the more significant bit for a left movement. For any kind of a left shift, which you see in the top box there, where it shows 0 or 1 pointing to bit 0, a left shift is always going to shift from the least significant bit of the specified element, in this case any array 0, to the more significant. Now in this case we're showing a shift of all 96 bits. Starting at bit 0, everything of any array 0, everything is shifting to the left all the way through to the end of the third dent, and then bit 31 pops out the end into bit space. However, when you think about the actual movement of values, you don't want to overwrite an existing value before you've shifted it. If you were going to consider the sequence of the top block there, the top diagram with the green arrows, the first thing that's going to happen is bit 31 of any array 2 is going to pop out into bit space. Then bit 30 is going to move into 31, 29 to 30, 28 to 29, and etc. all the way over to the right. Bit 0 of any array 2 is going to move into bit 1, and then bit 31 of any array 1 is going to move into bit 0 of any array 2, and so forth, all the way back to the beginning of any array 0. When bit 0 of any array 0 moves into bit 1, right next to it, then a new value is going to be pulled into bit 0 of any array 0. It could be a 0 or a 1, whatever the value is for your source bit. The next diagram would be a right motion. It just happens to be to your right, but don't depend on that when you're looking at your logic. The first movement is going to take bit 0 of any array 0 and out into space it goes. Then bit 1 of any array 0 will move into bit 0 of any array 0. Then 2 to 1, 3 to 2, 4 to 3, 5 to 4, and so on, all the way until 31 of any array 0 moves into 30, and then bit 0 of any array 1 moves into bit 31. And so forth all the way through any array 1 and then into any array 2 until you move bit 31 of any array 2 into bit 30. Then the next step is to take and put a new value into bit 31. Now this is if you were shifting all 96 bits. And since we have 3 dents, this is the maximum size of shift that you could do, would be 96 bits or less. Here we're doing less. Here we're working entirely within any array 1. In other words, any array 0 and any array 2 are not in the definition of our bit shift instruction. So the bit shift instruction has nothing to do with, no effect on, etc. any array 0 or any array 2. It's all within any array 1. If we're doing a left motion, that means that if we're doing a left motion, then we're going to unload 31, bit 31 of any array 1 out into bit space, or that could be the actual unload position if we're actually using a 32-bit bit shift instruction. So we move that out to the unload position and out into space, and then we move 30 to 31, 29 to 30, etc. all the way until we get down to bit 0 into bit 1 position, and then we pull in a new value into bit 0. Consequently, the same thing with the bit shift right. If we're starting from the right, then we're moving. If we're doing a right shift, we're starting from the left. The actual first motion is for bit 0 of any array 1 to go to the unload bit and to disappear into space. So we unload it into the unload bit, but it also goes off into space because it doesn't shift from bit 0 of any array 1 to bit 31 of any array 0. It doesn't go past the boundary of the definition for this shift. These two diagrams right here aren't 100% relevant to most bit shift instructions, other than if you keep the shift, whatever number of bits, within one element of this array, then depending on what direction you're shifting, if you're shifting left, then each new value that leaves 31, in other words, when you have another shift, 31 is going to go into bit space, even if you're unloading anywhere in between. So at the far end of the boundary, in the direction you're going, if you're going left, then the boundary is at bit 31. So bit 31 has no place to go. That value is permanently lost each shift, regardless of whether it's unloaded or not at that position. It still does not continue going left to the next position, which would be any array 2. So we're not pulling, now listen close, any array 0, bit 31. That does not get pulled into any array 1, bit 0. And any array 1, bit 31 does not go up to bit 0 of any array 2. That is, if the length of your defined instruction is 32 or less and you have specified any array 1. I don't have to say all that about the second diagram. It's the exact same thing, with the exception that you're going right instead of left. New values come in at the more significant position, and when they get to bit 0 on the next shift, they can get unloaded there, but regardless, they're going to disappear. They're not going to transfer from bit 0 of any array 1 to bit 31 of any array 0. Just keep that in mind. If you have a length of 32 or less, then it's all going to stay within that element of the array. It will not go from any array 1 right to 0 or left to 2. Now here we have, this is more applicable to what you did in the lab project. And in this case, we're using a length of 6. These diagrams are really identical to these in the sense, if you look at just any array 1 in both cases, and then you look here, it's the same length of bits moving. So for a left shift, if we have a length of 6, then we are really only working with bits 0, 1, 2, 3, 4, 5. That's 6 bits, length of 6. Now, whatever values that we're bringing into bit 0 and then shifting left, when they get to bit 5, that's the end of the length. The very next shift is going to take whatever value is in bit 5 and move it to another bit location in memory, the bit shift left unload position. And that BSL, that's in lieu of the actual name of your control tag for the bit shift left instruction. So I just put BSL.ul to indicate the unload bit for that instruction. Now that value that's in 5, bit 5, when it gets unloaded to the unload bit, it also shifts to bit 6. And as you keep executing the bit shift left, pulling in new values at 0, unloading them at 5, they don't disappear instead of going to 6. They go to 6, 7, 8, 9, all the way down to the end. And when they get to the limit of that element, of that array, then they off into the bit space they go. They don't go from bit 31 of any array 1 into bit 0 of any array 2. So you see, looking at boundaries of these elements, these 32-bit dents, in a linear fashion like this, makes more sense than it did looking at them like this. It's best to illustrate them in a linear fashion. And then on the bottom, you have the bit shift right, and the only difference between a bit shift left and a bit shift right is the position of the unload and where new values are pulled in. So if you're going left, new values are always pulled into bit 0, and whatever the length is, in this case 6, they're unloaded at that position. But they keep on going across that double integer until they disappear when they leave bit 31. With the bit shift right, the bits are, new values are pulled in at 5, bit 5, and as they shift, every time you do a shift, bit 0 value goes to BSR unload bit, and off into bit space it goes. It doesn't go from bit 0 to bit 31 of the lower element. In the upper diagram with the bit shift left, once the value gets shifted from 5 to 6, it keeps on going across until it gets to the end. Bit 31, then out it goes. With the lower diagram, bit shift right, if you happen to have values, we tend to think of 0 as nothing and 1 is something. Well, 0 is an actual value, and so is 1. 0 can mean the presence or absence, and 1 can mean presence or absence. It just depends on your philosophy on how you want to use bits to represent things. You may want to represent a part going through a line that needs a part with a 0, meaning it doesn't have the part. So if without a 0 there, you're not going to get the part added to that larger assembly. The bottom one is a little bit more, takes a little bit more thinking about, because there really shouldn't be any values in bits 31 through bit 6 of that lower any array 1, because you're not putting in any values. So they should start out all zeros, so you should see nothing but zeros marching across to the right. However, in the lab project, I did have you put a bit value of 1, I think in bit 6, and then execute it. And if you put it in 6, 7, and 8, as you execute it, whatever value is your source bit is going to override whatever goes into 5, no matter what, is shifted from 6 to 5. What is in 6 through 31 is almost irrelevant. But as far as pure behavior goes, any values that are in 31 down to 6 will continually shift with each bit shift right instruction execution, but bit 5 will always be overwritten with whatever the value is in the source bit. Let's say, now in this example, we're using a length that's less than 32 bits. With a length of less than 32 bits, as I told you, nothing is going to leave this 32 bits from any adjacent element. And nothing within this 32 bits, any array 1, is going to leave and go to 2 or 0. So nothing comes in from 0 or 2, nothing goes out to 0 or 2. However, if you make a length greater than 32, in this case it looks like we have 35. If we do a bit shift left, the most significant bit of this shift or this length is going to be bit 2 of any array 2. Starting with bit 0 of any array 1, that's the first bit. And that's something that does trip us up when bit 0 is the first, bit 1 is the second, and so on. So any array 1 has 32 bits. Then you have 0, 1, and 2 of any array 2. That adds up to 35 bits. So the length of this shift within this array of 3 dents is 35 bits. The specified element for the shift is any array 1. So it's going to start at any array 1 bit 0 and shift to the left. When it gets to the 35th position, which is bit 2 of any array 2, it's going to unload whatever's there. Each shift is going to unload to that bit in that data structure, that control tag data structure, in this case named BSL for bit shift left. When bit 2 of any array 2 unloads, it's also going to shift to 3, then 4, and so on, all the way down to the end of any array 2, and then go off into bit space. Now let's do it the other way, going right. Again, as we said before, if we shift right inside of one of these elements, all the bits shift But in this case, because our source bit is pointing to bit 2 of any array 2, because we defined our length as 35, then on every shift, even though we're shifting any array 2 to the right towards 0, our source bit is going to override whatever's in bit 2. And then it's going to go to 1 to 0, then it's go to 31 of any array 1, and so forth, all the way down to the end. Whatever is in bit 0 of any array 1 at each shift will unload to the BSR unload bit, and instead of continuing to move through the array, it will off into bit space. It won't go from bit 0 to bit 31 of any array 0. One thing that we're doing different in volume 1 than we did, in volume 2 that we did in volume 1. Really, volume 1 is called beginner, volume 2 is beginner plus. In the first volume, we spent a lot of time discussing the graphical user interface, RSLogix 5000, and how to create rungs, edit rungs, modify rungs, move rungs, duplicate rungs, etc. We're not doing that as exhaustively in this volume. In the manual, we do show you how to create rungs. We do have some step-by-steps. In the videos, we're not going to discuss all those details. We're going to talk more about the results and the logic and how the logic behaves. Then we're going to actually show you step-by-step with me moving the mouse and the mouse pointer and creating rungs. On occasion, I may do it if I see some intrinsic value. Bit shift left. This is the first of the bit shift instructions. These instructions shift the value of a bit to an adjacent bit position. While doing that, they shift all the other bits in a direction left or right specified by the instruction. The stream being a specified array in memory with a specified length of influence. The length must respect the total length of the array, and the length specified in the instruction should also respect the boundaries. There are two approaches available to you when visualizing the behavior of memory locations affected by the bit shift instructions. We showed those to you just a little bit ago. The physical array, a stack of double integers. When the bit shift left, the most significant bit value moves to the least significant bit position of the next highest double integer in the array. The least significant bit of the lowest double integer sucks in a 0 or 1 from the source bit. And the most significant bit of the highest double integer pops its value out to wherever it came from. We say bit space. Another approach is a linear array, a row of dents. When the bit shift left, the most significant bit value moves to the least significant bit position of the next highest dent of the array. The least significant bit of the lowest dent sucks in a 0 or a 1 from the source bit, and the most significant bit of the highest dent pops its value out to wherever it came from into bit space. I had several diagrams in the manual to illustrate this. And I want to remind you again that a left shift moves the least significant towards the more significant. If we look at our data table, our program tags data table, there's any array 0. Most of our exercises we're doing with any array 1. We're doing with any array 1 with a left or a right shift that's less than 32 bits in length. Everything's going to take place within these 32 bits right here. Any array element 1 bit 0 through any array element 1 bit 31. A left shift would be downwards in your display here. It would be from the least significant bit 0 towards the most significant bit 31. I had you decrease this array to 3 elements from 10 elements. These 7 rungs here should match the logic that you had when you did the first lab project in the bit shift left section. We had you add the rung at the top, rung 0, as a quasi HMI, human machine interface, so you could observe the motion of the bits as they shifted to the left or eventually to the right. In that rung, in the lab book, you may have entered it with something different, with an OTE instruction that says nothing. You could also have used a no op or no operation instruction, which is under the program control right there. No op and always false. These are two lesser known but very useful instructions. And always false, you can put that anywhere in the rung and make the rest of the rung false. The no op can go at the end of the rung or anywhere in the rung, and it's a no operation. So the only purpose of rung 0 here is for you to see the state of those bits. We have the last or most significant bit of any array 0. That way we can set this one to 1 or turn it on to see if it gets entrained into the shift. And it's a matter of opinion whether you have the source bit second or first in this rung. I'm going to move it to the first position here. It really doesn't matter because this rung is not executing any logic. It's simply for display. If I turn on my source bit, you see that it's now highlighted. And this would be the last bit of element 0 and the first bit of element 1. So going from bit 31 to bit 0, and then in sequence 0, 1, 2, 3, 4, 5, 6. Since we're doing a length of 6, then this would be the last bit in the shift area. This bit is there for you to see what happens when you shift out of the last position into the unload bit. And down here we have the unload for to the left. That's the name of our bit shift left instruction. The control data type is, the instance is called to the left, and here is the unload bit. So when this comes on, we turn on light number 2, or it's the third output local 10 data 2. You can obviously see that you unloaded a 1, but keep in mind, every time you exercise this bit shift left, whatever is in this position, a 0 or a 1, gets unloaded to this bit. We tend to work with 1s because it's easier to see the shifting, even though the 0s shift equally as well as the 1s. I then had you turn on the source bit and leave it on. First I had you test it, then I had you just leave it on. So right now, if we were to execute a bit shift left, a value of 1 is poised to go into the first position. In the lab project, I said to toggle the enable bit, which is bit 0, on and off. Now, I didn't leave it on long enough for you to see that this went on, but it did. But you can see it took that value and shifted it into the first bit of that element. What you didn't see was that 0, before that happened, whatever was here went to the unload destination position, then 4 went to 5, 3 went to 4, 2 went to 3, 1 went to 2, 0 went to 1, and then this value came in there. If we wanted to do that over, I can toggle this bit off. We're back to where we started. And just for grins, I will toggle that bit on. Okay? So you can see that the last array bit is on. So if what I say is true, when I do the enable bit shift left, and just to prove that, I'll use the toggle switch instead of the push button. So I'll flip that on and leave it on. And so you see what happens is several things. One is that we unloaded bit 5 into the unload bit, and you see it turned on. Also, when it unloaded from 5, because it's shifting the whole element, every time you do a bit shift left, it shifts any array 1 bit 0 through bit 31, it shifts it to the left, from the least significant to the most significant. Which means the value of 1 that wasn't 5, it went to unload, but it also went to 6. That's why we put bit 6 in here. It's not part of the shift, but it is part of the word, so you can see that the bit does continue on. Now, that's not what we wanted. We didn't do that as part of the lab at that point, so I'm going to toggle that back off, toggle this back off, and I'm going to toggle the unload bit off because that's the way it was when we started. So now I'm going to do that shift again. That's what we did in the manual, and it shifted a 1 into position 0, or bit 0, the first position in the shift. The question in the manual, ignoring the source bit, how many additional, if any, bits change state? Be careful with your answer. Some things appear in more than one place. Well, 2 bits. Local 1, any array 1, bit 0 changed state, and so did local output data 0, this bit right here. The reason that I include, and by the way, if your answer was 1 bit and you put any array element 1 bit 0, that is correct. But this bit also changed state. And these two right here are exactly the same. First array bit is aliased to any array element 1 bit 0. So both of these tags here address the same bit in memory. When this bit went to the on state, so did this, so it changed state. So 2 bits change state, but I would accept either answer as correct, 1 or 2, as long as if you put 1, you were only thinking of the bits in the shift field of 6 bits, but if you were thinking of all the logic, then 2 would have been the correct answer. And then I said trick question, did you see any bits shift? Well, you did not see any shift, but you did in a sense. You saw the value from the source bit shift into there. Now I don't know if you want to call that a shift or not a shift. It copied the state of this memory location into this position. It wasn't really a shift. So I would say the answer is actually no for that question. Then I had to change the source bit field device back to the off state. So we flip input 1 back to the off state. Then we enable the local 1 iData 0, which is the enable bit shift left, on and off once. Now I have push buttons and toggle switches wired in parallel. We're using the digital field device simulator, universal digital field device simulator, to do our lab projects with. I can choose to use the toggle switch for a maintained on-off, or I can use the push button wired in parallel with it, which functions not only as a normally open, but also as a normally closed. If I go back here to the source bit, right now I have bit 0 turned on here, the enable bit shift left. In that position, if I push the push button right next to it, see, it's normally closed. If I let go again, it goes true again, and notice it shifts to the next position. Now that's not what we did in the lab, so I'm going to toggle that off, toggle that on, and turn the enable bit shift left so we're right back to where we're supposed to be. So it shifted from 0 to 1, from the first position to the second. Ignoring the source bit, how many additional, if any, bits change state? Well, I would say this went from on to off, this went from off to on, and this, for the first array bit, that went from on to off. So there were 3 bits. Did you see any bits shift? Well, you can say no, you didn't see them shift, but you saw them change state, which is the same, I guess, as saying they shifted. For that question, you could say no or yes. No, because you don't actually see it, the bit drifting across the page from one position to the next. And you could also answer yes, and then the other question would be from element 1 bit 0 to element 1 bit 6. So you saw them shift in this direction. You can see the 1 moving, but you didn't see the 0 move here to here to here to here, because you would have to have alternate states in order to see that. That would be impossible to see. Toggle the enable bit for the BSL on and off once and then leave it off. How many bits, if any, change state? Two of them did. Element 1, bit 1, and element 1, bit 2. Did you see any bits shift? You could answer yes or no. I would accept both of those. If you said yes, then you should have said from 1.0 to 1.6. Now, if you said from 0.1 to 0.2, and in the previous question, 0.0 to 0.1, that would be a legitimate observation because you can't see the zeros shifting. And if you had two ones in a row, in other words, if both of these were on and then you shifted, then 1 would shift to 2 and 0 would shift to 1. So you could answer yes. Whether you put yes, 0 through 6 shifted, or yes, 1 shifted to 2, you made the correct observation. Repeat the momentary on state of the enable tag until the single on state has reached the end of the length of the shift. Be careful not to go past. If you do, you need to toggle input 5 down here, clear reset, and start over. I'm going to toggle that. I'm going to toggle this bit right here until I turn on any array element 1 bit 5. Okay, that's the last bit in the shift range, so to speak, the length of 6. Did the single on bit shift across rung 0 to the 6th position? Yes, it did. And that 6th position is element 1 bit 5. Did the bit unload? Well, you could answer that yes or no. No is probably the most apparent answer because you didn't see the unload bit come on. But it actually did unload because what was in bit 5 here unloaded into the unload bit, but the fact that it was a 0, you didn't see any change. On each execution, it unloads. So it always unloads. If you do a bit shift left, it's going to unload. Whatever's in 5 is going to unload down here to the unload bit. This single on state did not unload, and that's not until the next shift left. Okay, repeat that shift one more time. And now it did unload, and you see the unload bit is on, and the bit also moved into position 6. Is the last bit in the shift register still on? No. The last bit in the shift register would be element 1 bit 5. Did the unload bit turn on? Yes, it did. Is the bit past the end of the defined length on or off? It's on. Bit 6 is on. Then I had you open up your control, or rather your tag database, and then expand any array 1 and ask you if the bit pattern here matched what's in the manual, matched what you had. Now the easiest way to see that is to look at the actual double integer value. This 64 represents the whole 32 bits. See, if I bump that up to 1, I'm going to add 32. So I'm going to put a 1 in there, hit enter. See, now it's 96. Because that binary-wise is worth 32 decimal. So we'll go back to what it's supposed to be. So if you had 64 here and you had bit 6 on, which matches the logic, then your answer would have been yes. Then I had you go down to the end of array 1 to see if anything slipped from element 1 to element 2, and of course it did not. Enable the BSL, the bit shift left, one more time. Okay, we'll go back up here, and we'll go back to the logic. Go to Window, Main Routine. So there's that single state, and we're going to shift one more time. And now you see it shifted from 6 to 7. Shifted from 6 to 7. This isn't exactly what I had you do in the book, but this is good. See, it's in bit 7 now. What I had you do was to continually shift until this one moved all the way down to bit 31. So I'll do that. I could easily have just changed the 1 to a 0 and then changed bit 31 to 1 and done the same thing. But you see I'm shifting. It's in 28, 29, 30, 29, 30, 31. So now I'm in the last position. Now it says enable it one more time. Now there's two places you can look at this. You can look at it here, or you can go back to the logic, because that's why we put that instruction in there. So I'm going to shift it one more time. You see nothing went into any array 2. If I go back to the program tags, we had a 1 right here. I can change that to a 1, enter. I can do this again. So I'm going to hit shift again, and to prove that this is the boundary and it won't shift into the next double integer unless that double integer is included in the shift field. I hit shift, you see it disappears out into bit space. It went. Then I had you go back to the logic, toggle this bit on, well, this one right here, toggle this one on. Then I had you do the bit shift left and watch to see this is the last bit of any array element 0. Look to see if it shifts into the very next bit in the array, which would be element 1 bit 0. You see it doesn't. You can see we're doing this right now. All we're doing is shifting zeros through that. Every time we turn this on, it shifts bit 31 out into space, 30 to 31, 29 to 30, 28 to 29, etc. But they're all zeros, so you don't see anything, but they are shifting and they are unloading. I'll turn that back off by way of the keyboard. Did the last bit of the previous dent shift into our defined length in the element any array 1 into bit 0? No, it's outside the instruction definition. So the instruction definition here for a bit shift left would involve any array element 1 and higher. It would never involve anything in any array element 0. It's outside the instruction configuration. What are the boundaries for state changes affected by the BSL instruction? Well, they would be any array element 0 to any array element 1 bit 31. That is, any array element 1 bit 0 to any array element 1 bit 31.